All right, folks, I wanted to talk through what we looked at on Thursday in case you were not able to make it to live class. Our topic was dealing with data. And so we spent a lot of time talking about the rules for graphs. So we started off by brainstorming some rules for making graphs in science. I'm sure you know a lot of them, things like labeling your axes, knowing where your independent and dependent variables go, putting on a title, making sure the data fills the graph and it's not zoomed way in or zoomed way out, making sure you have units on your numbers. All of those sorts of things you've learned in other classes, and I wanted to extend things a little bit and talk about what's specific to physics. So as we look at things today, our goals are going to be to talk about what we mean by sufficient data or enough data, how we represent uncertainty in our data, how do you display a data to see a trend, and what we mean by the slopes and y-intercepts, how we can interpret those values. At the end, we did a group assignment that I will present on here, and you can try out and see what your answers would have been. So first topic was sufficient data, and we looked at these two graphs. They're looking at the same experiment, so measuring the temperature of a cup of coffee as time goes by. Student A measured 2 different times. They did the experiment 5 times and averaged their results. So they took 10 data points and arrived at this graph where they had averaged their results. Student B only did the experiment once, but they took data at 10 different times instead of 2 different times. Looking at these graphs, which one seems better? All right, when you look at this, you can really see a trend much more clearly in data B. Even though both students took the same amount of data, being able to see a wide spread in the data makes it really helpful to be able to see trends in data. So when we look at how much data is enough data, we sometimes use the rule of 10. And in physics, what we usually mean by that is that ideally you would have 10 different values for your independent variable. Fewer values of your independent variable can make the trend difficult to see. Like in graph A, you can tell that it's decreasing, but is it a straight line? Is it a curve? In graph B, when you had at least 10 data points, you can see much more clearly if it should be a straight line or a curve for interpreting the data. Okay. In lots of other scientific disciplines, testing each independent variable more than once is really important. And we talked about, for example, in biology or medicine, if you're testing a medication like a vaccine, you want to test it a lot of times the same way to make sure there aren't problems and that it's effective. However, in physics, if you're timing something that's happening over a period of time, sometimes it's really difficult to do more than one trial, and it's better to get a large number of independent variables over a wide range rather than testing each value of the independent variable hundreds of times. Okay, so that's what we mean by sufficient data and having enough data. All right, 2 more graphs that we kind of compared and looked at. Both of these graphs show a person's weight and age tracked and recorded. And we wanted to say, first of all, what's the difference between those 2 graphs? What's the difference between the data and which one is better? Okay, so taking a look at those graphs, if you look at the horizontal axis, they're both age, but one is measured in years and goes from 0 to 65, 70 years. The other one is measured in months and only goes up to about 18 months. So one tracks over a person's entire lifetime. The other one is only tracking until they're about 1.5 years old. The y-axis on graph C goes all the way up to 150 pounds. And on graph D, we only go up to about 25 pounds. Okay, so which graph is better? Okay. The conclusion we really came to is that it really depends on what you're looking for. If we consider graph D, for example, this is a great graph and it's super helpful if we're interested in growth of a person as an infant. And we want to know as a baby, what was their growth rate? Were they growing well? What do we expect for infants? But if we want to know the range, or we want to know someone's weight over their entire lifetime, and we try and extrapolate from this data, we only tested data through about 18 months. If we draw a line that fits that data well, but goes out to 300 months, that's like 25 years. What this is telling us that at 25 years or 300 months, this person would weigh 300 pounds, and it would just keep increasing at a similar rate. So at 50 years, they would weigh 600 pounds. And that's not really probably a good conclusion to draw. And so we said that to be valid over a range of data, samples should be taken throughout that entire range of independent variables. So if you want to be able to predict something 25 years down the line, you shouldn't stop collecting data at a year and a half. You need to collect data closer to where you're going to be making a prediction. Now, sometimes the reason we're collecting data is to make a prediction of something we can't see yet, but we want to be as close as we can to the time frame or the scale of the independent variable that we're trying to make predictions with. Okay, and that's what we meant by having an adequate range of data. Okay, so sufficient data, ideally 10 different values for your independent variable, and what range of data you take impacts the range where you can make accurate predictions. So two things to be thinking about as you're collecting data for the labs that we're doing in class and kind of going forward in physics. Okay, the second topic was looking at uncertainty in data. So we looked at this diagram. We have a ruler here measured in centimeters and a pencil sitting on top of it. We want to know how long is the pencil. So kind of in your head, think about what would you write down as a measurement for that pencil? Okay. And in class, a lot of people said 6.6 centimeters, 6.7 centimeters, 6.5 centimeters. The uncertainty that we have in that data and what we write down for a measurement is partly determined by the measuring device. So this ruler is marked at every centimeter. So we know for sure that this is between 6 centimeters and 7 centimeters. The digit beyond that, the one in the tenths place, is an estimate. So we're guessing that looks like a little bit more than a half, so maybe 6.6, maybe 6.7. We're guesstimating that tenths place digit, which means we are estimating one digit past the last marking on the ruler. That means that that last digit is what we call uncertain or estimated, and sometimes we'll write it like this: 6.6 centimeters plus or minus a tenth of a centimeter. That tenths place is uncertain. It could be as much as 6.7, as little as 6.5, but it's in that range. I think the best measurement is 6.6, but it might be a little bit off, okay? And that indicates the amount of uncertainty in our data. You've probably seen something like this in other classes, but the measuring device isn't the only thing that determines the uncertainty in a data. The other thing is how you're measuring the data, your measuring method. So consider using a stopwatch. Okay, there's a picture of a stopwatch here. It has a measurement shown on there of 1 minute, 23.44 seconds. Okay, now think about how you use a stopwatch. You're holding it in your hand, you click to start, you click to stop, which means you're relying on your human reaction time twice, once to start it, once to stop it. And human reaction time between when you see something happen and when you can react to it is about 0.2 to 0.3 of a second, 0.2 to 0.3 seconds. Which means when you use a stopwatch to start and stop, that's about a half second of uncertainty in your data. You timed it, but it might be up to a half second more than that time or a half second less than that time simply by using a stopwatch. Okay, so when we look at this, that hundredths place that the stopwatch is telling you is really kind of absurd. We don't even know that the 0.4 is accurate. It could be as much as 0.9 or as little as 22.9 seconds. And so rounding that to the hundredths place is just an absurd amount of accuracy. We don't have that precision in our data. So when you write something, for example, off a stopwatch, you have to know what the uncertainty is in the measuring method. And what you should write down for this measurement is 1 minute, 23.4 seconds, plus or minus half a second. Okay. The other thing that we'll see a lot in physics is we're measuring something that's moving, right? Physics is a lot about the study of motion. So we're measuring things that are moving all the time. And if you're trying to pinpoint the measurement in real time as something is happening, there are a lot of sources of error in that data. And you're going to have to use your judgment to consider how off do you think you might be, right? So as you're watching this, do I think I might be off by a centimeter, even though this is a ruler that's marked to tenths of centimeters? Do I think I might be off by 5 centimeters, half a meter? Where do I think that I'm approximating between? And a lot of that uncertainty when we're talking about moving objects comes from your method of measuring and your own personal judgment. As we're doing some labs where you're looking at video data and you can pause the video and you can go forward one screen or backwards one frame, there's a lot more precision than if you were trying to do this live without a video, right? So some of the labs we do in class where we're looking at videos, you'll have much less uncertainty than you would if we're doing them in class. Okay, looking at trends in data. When you plot data, and you want to make a graph so that you can see the overall trend in the data, graphs are a great way to do that. So looking at this data, this is from a pendulum lab that you may have done in another class at some point. You're swinging a pendulum and measuring the period. So how long does it take to go back and forth once? Then you're changing the mass of the pendulum. This one goes from 20 to 100 grams. We're measuring the period. What would you say about the trend of this data? Most people will look at this graph and say, okay, well, as the mass increases, so does the period. Okay, and I think that's a pretty, just by looking at the graph, that's what it appears. This is why we have to be careful in when we graph data that we are accurately representing the trend, because we just talked about the uncertainty in measurements. If you're timing something with a stopwatch, you have about a half-second uncertainty. Okay, we can represent uncertainty in data using what we call error bars. So these points all have these little wings sticking up from the top and the bottom. Those are what we call error bars. And those indicate that, for example, when the mass was 80 grams, the period was 6 seconds plus or minus half a second. So it could be as much as 6.5 seconds. That's why the bar goes up to 6.5. It could be as little as 5.5. So those wings show the range that that data point could actually be. We think it's right in the middle. That's our data point that we measured, but it might be in that range. That's our uncertainty range. And error bars give us a way to sort of visualize that when we look at data. So when we add the error bars, we still might think this is an increasing trend. But I want you to notice something. I can draw a line with a negative slope that's within the uncertainty of all that data, right? That green line shows a negative slope. And this shows that within the margin of error, within the uncertainty in our data, this could be a decreasing trend, right? We can't rule that out based on this data because that's within the uncertainty of our data points. Okay. The other thing that you would want to think about as you're displaying this data is where your graph is starting. If you look at the bottom left-hand corner of this graph, it's not starting at 0, 0. And in fact, if you look at the scale on the y-axis, you see that this is really zoomed in from 5.5 to 6.75. That's barely a second. And if we change the graph just a little bit and make the left-hand corner the origin, so 0, 0, our graph now looks like this. Okay, that's a strikingly different graph than what we saw on that the first slide of this data. It's the same data, it's the same error bars, but now when we draw the line of best fit, maybe it's positive. That's what we kind of drew on that first graph. But we can see clearly, yeah, it could be negative. And probably the best conclusion from this data is that this is a flat line. There's not a relationship between mass and period based on this data. Okay, and I wanted to highlight this as an example because the way you display your graph can really impact what that trend looks like. And so you have to look at some things about how much is the uncertainty? Am I displaying the origin? Should I display the origin 0, 0 on my graph? Should I make sure that it's not way zoomed in? Or does it need to be zoomed in? And those are things that you're going to have to look at your particular experiment and make as a judgment call. Okay. In physics, in addition to saying a trend is increasing or decreasing, we are going to be looking at some specific numbers. We're going to be spending a lot of time looking at lines of best fit and interpreting them. So if you're graphing on Google Sheets or an Excel spreadsheet, This is called a trend line for the graph. And this really just means the line of best fit, or the equation of best fit if it's not linear. Google Sheets displays it as you see here. The line of best fit, the equation of best fit is at the top of the graph. And if you're not sure how to make that appear on your graph as you're graphing things, look back at the graphing data video, and I go through how to get that to come up when you're working with a Google Sheet. But this equation of best fit, or EOBF as I sometimes abbreviate it, it leaves out the y equals, but it means that the line of best fit on this graph is y equals 0.915x minus 2.57. Okay, now let's look at this data. What are we looking at on this graph? Well, this graph is showing us the hours of homework and the number of classes that you're taking. So when we write down X and Y have specific meanings because this is science and this is an experiment. So when we talk about Y really means the hours of homework, and X really means the number of classes. So I'm going to ask you, when you write down your equations of best fit, to use variables that are meaningful based on what your data is. So hours of homework, maybe H is a good choice, and number of classes, maybe we'll use N, H for hours or homework, N for number. And so I would ask you to write your equation this way. H equals 0.915 N minus 2.57. Okay, and that gives us an equation of best fit where we know what the variables mean. We can recognize that this is a relationship between homework and N number of classes. Okay, but we're not going to stop there with our line of best fit. We can get a lot of information from these equations. So looking at this equation, H equals 0.915 N minus 2.57, the y-intercept has a specific meaning according to the data. So the negative 2.57 shows us where this line crosses the y-axis. Okay, so way over there on the left side of your graph, we're saying that when your number of classes is 0, your hours of homework is negative 2.57. Okay, so if you wrote that as a sentence, the meaning of the y-intercept as a sentence would look like this. If you took no classes, there would be negative 2.57 hours of homework. Okay, that's what our y-intercept means. Now, that doesn't make actual sense. You can't have negative hours of homework. And so that's important to know. It's important to know this is what my y-intercept means. And does that physically make sense? Okay, and in this case, it doesn't, right? You can't have negative hours of homework. You would expect that when you take 0 classes, you would have 0 hours of homework. Okay, and it's important to know because that means that a couple of things. Maybe this line of best fit is only valid down to 2.5 classes. That looks like about where it's crossing the x-axis, right? Maybe this means that this should really be a curved line, right? I don't think so, probably for this data. But maybe it should curve and have an asymptote, or it should cross at 0, 0. Maybe it should cross at 0, 0 and have a slightly different slope or be shifted up. But it's important to know what that y-intercept is telling you and if it's a reasonable thing or if it's not a reasonable thing, okay? The other number in our equation is our slope, the 0.915. So think about back to math class. How do you calculate slope? Slope is always rise over run. So the change in y divided by the change in x. In this graph, we're talking about the change in hours of homework divided by the change in number of classes. Okay, now, if you're trying to write this as a sentence and say, what does this mean? Replacing the divided by with the word per can be really helpful. So we're talking about hours of homework per class. Okay, well, that's something that makes a lot more sense. This is the hours of homework I would expect per class that I'm taking. And if I write that as a sentence, I would say the meaning of my slope is that I should expect 0.915 hours of homework per class that I'm taking. Okay, and that gives us a lot more specific interpretation of our data than just saying, if you take more classes, you'll get more homework, right? We can be a lot more specific about that and use that to make a more accurate prediction. And knowing the meaning of the slope and knowing the meaning of the y-intercept is going to be something we keep coming back to in physics and keep looking at interpreting those numbers and saying, what is the meaning of the numbers? We know when you take more classes, you're going to get more homework. We don't need to collect data to know that. The data helps us know and predict, well, how much more homework am I going to get? How much more distance is this car going to cover? And that's what we're going to be looking at when we interpret slopes and y-intercepts. Okay, a chance for you to practice this on your own. In this setup, we have students that are rolling a ball down a ramp, and they're measuring how long it takes the ball to get down the ramp. Then they're changing the angle of the ramp and measuring it again. So they've changed the angle from, looks like 10 degrees to 50 degrees, making that steeper and steeper, and then measured the time that it takes to roll down the ramp for each one of those. Okay. They've obtained a line of best fit that's given at the top. Y equals negative 0.0529 times x plus 4.04. I want you to look at this data and I want you to write down a couple of things. I want you to write down what is the equation of best fit, looking at variables that are more meaningful than x and y. What does the slope mean? Write that as a sentence. And what does the y-intercept mean? Write that down as a sentence. Okay, so leave this slide up, pause the video, write those things down, and then come back and check to see if you've got something that matches what we said in class. Thanks and have a great day.